The entire project was to cover 200 acres and include housing for 2,000 employees of the facility. Tesla estimated that the tower would emit a wave complex of a total maximum activity of 10 million horsepower. The top of the tower was outfitted with a platform that may have been intended to accommodate powerful ultraviolet lamps, which Tesla could have used for an experimental beam system of electric power transmission that was on his mind. The tower structure and building beneath were built and partially equipped, but they never saw operation. From a museum at Wardenclyffe, the creation of a monument to Nikola Tesla. The year was 1900, and following 9 productive months of wireless propagation research in Colorado, Nikola Tesla was anxious to put a mass of newfound knowledge to work. His vision focused on the development of a prototype wireless communications station and research facility, and he needed a site on which to build. In 1901 he cast his eyes some 60 miles eastward to the North Shore village of Woodville Landing. Only 6 years before the North Branch of the Long Island Railroad had opened, reducing travel time to the locality from a horse-drawn 5 hours to less than 2. Seeing an opportunity in land development, a Western lawyer and banker by the name of James S. Warden had purchased 1,400 acres in the area and started building an exclusive summer resort community known as Wardenclyffe on Sound. With an opportunity for further development in mind, Warden offered Tesla a 200-acre section of this parcel lying directly to the south of the newly laid track. It was anticipated that implementation of Tesla's system would eventually lead to the establishment of a radio city to house the thousands of employees needed for operation of the facility. The proximity to Manhattan and the fairly short travel time between the two, along with the site's closeness to a railway line, must surely have been attractive features, and Tesla accepted the offer. The Wardenclyffe World Wireless Facility as envisioned by Tesla was to have been quite different from present-day radio broadcasting stations. While there was to be a great similarity in the apparatus employed, the method in which it was to be utilized would have been radically different. Conventional transmitters are designed so as to maximize the amount of power radiated from the antenna structure. Such equipment must process tremendous amounts of power in order to counteract the loss in field strength encountered as the signal radiates out from its point of origin. The transmitter at Wardenclyffe was being configured so as to minimize the radiated power. The energy of Tesla's steam-driven Westinghouse 200 kilowatt alternator was to be channeled instead into an extensive, underground radial structure of iron pipe installed 120 feet beneath the tower's base. This was to be accomplished by superposing a low-frequency baseband signal on the higher-frequency signal coursing through the transmitter's helical resonator. The low-frequency current in the presence of an enveloping corona-induced plasma of free charge carriers would have pumped the Earth's charge. It is believed the resulting ground current and its associated wave complex would have allowed the propagation of wireless transmissions to any distance on the Earth's surface with as little as 5% loss due to radiation. The terrestrial transmission line mode so excited would have supported a system with the following technical capabilities: establishment of a multi-channel global broadcasting system with programming including news, music, etc., interconnection of the world's telephone and telegraph exchanges, and stock tickers, transmission of written and printed matter, and data, worldwide reproduction of photographic images, establishment of a universal marine navigation and location system, including a means for the synchronization of precision timepieces, establishment of secure wireless communications service. The plan was to build the first of many installations to be located near major population centers around the world. If the program had moved forward without interruption, the Long Island prototype would have been followed by additional units, the first of which being built somewhere along the coast of England. By the summer of 1902, Tesla had shifted his laboratory operations from the Houston Street Laboratory to the rural Long Island setting, and work began in earnest on development of the station and furthering of the propagation research. Construction had been made possible largely through the backing of financier J. Pierpont Morgan, who had offered Tesla $150,000 towards the end of 1900. By July 1904, however, This support had run out, and with a subsequent major downturn in the financial markets, Tesla was compelled to pursue alternative methods of financing, with funds raised through an unrecorded mortgage against the property, additional venture capital, and the sale of X-ray tube power supplies to the medical profession. He was able to make ends meet for another couple of years. In spite of valiant efforts to maintain the operation, income dwindled and his employees were eventually dropped from the payroll. Still, Tesla was certain that his wireless system would yield handsome rewards if it could only be set into operation, and so the work continued as he was able. A second mortgage in 1908, acquired again from the Waldorf Astoria proprietor George C. Bolt, allowed some additional bills to be paid, but debt continued to mount, and between 1912 and 1915 Tesla's financial condition disintegrated. The loss of ability to make additional payments was accompanied by the collapse of his plan for high-capacity transatlantic wireless communications. The property was foreclosed. Nikola Tesla honored the agreement with his debtor, and title on the property was signed over to Mr. Bolt. The plant's abandonment sometime around 1911 to 1912, followed by demolition and salvaging of the tower in 1917, essentially brought an end to this era. Tesla's April 20, 1922 loss on appeal of the judgment completely closed the door to any further chance of his developing the site. Tesla, the father of radio, as we have seen, Tesla's earliest oscillators were dynamos, but, having determined that he could not reach the higher frequencies by this means, he went on to develop the spark gap oscillator, the Tesla coil, and the magnifying transmitter. But did any of these devices become the first to be used for overseas radio transmission? No. Ironically, the first commercial overseas transmitter was a 21.8 kilocycle Alexanderson alternator operated by RCA, a design evolved straight out of Tesla's early dynamos. Such was Tesla's luck in radio. Official histories often credit Tesla with the polyphase system and either ignore his later inventions altogether or dismiss them as the work of a crackpot. But among those who have published honest research on the subject, there is 100% consensus that Tesla was cheated out of his rightful place in history, particularly his status as the leading inventor of radio technology. Radio simplified. Early radio devices are fascinating and worthy of study, if only because they remind us that powerful radio technology can be so simple and accessible to anyone, the present-day micro-complexity notwithstanding. As we have seen, the earliest transmitters in wide use by amateurs were not alternators but spark gap oscillators. To get on the air, all you needed was a battery, a telegraph key, an induction coil, a spark gap, a length of wire as an antenna, and a ground. Of course, the addition of a capacitor juiced it up considerably. The very earliest experiments in radio receiving used a simple spark gap as a receiver. When you saw an arc across the gap, this was the detection of a disturbance in the medium. This evolved into a detector called a coherer. This is just a horizontal glass tube loosely filled with metal chips, iron, nickel. It is placed in series with a battery and a telegraph sounder, and one side of the coherer goes to the antenna, the other to ground. The coherer is a switch, a semiconductor, really, that conducts when there is a disturbance of the medium. The more easily conducted radio frequency energy triggers conduction of this almost conductive material. To get the coherer back to a non-conducting state requires a tap that can be accomplished manually or by mechanical linkage to the telegraph sounder. Tesla comes into the technology about here. He improves the coherer by putting it into continual rotation, rotating coherer, so it didn't need a tap to reset. Tuned radio. The spark gap transmitter was indiscriminate as to the frequency of the disturbance. It put out a dirty complex of frequencies consisting of a rough fundamental determined by width of gap, together with parasitic oscillations, harmonics, splatter, what have you. The coherer was set off by any disturbance. In Colorado Springs, Tesla used a rotating coherer to track electrical storms. The celebrated Marconi units employed nothing more evolved than this crash method of signaling. So why is Marconi so famous? It is because, like Edison and Westinghouse, he built up an industry around the invention and made himself famous in the course of promoting his enterprise. Marconi's company was ultimately incorporated into RCA, now incorporated into General Electric. It owed much of its technological development to ideas lifted from the likes of Tesla. Tesla's contribution was nothing less than selective tuning. He set forth the principle of resonantly tuned circuits in his Tesla coil patent of 1896. And the principles of transmitter-receiver tuned circuits a year later in his wireless power patent. The Tesla coil is a powerful and simple radio transmitter. If the primary circuit is smoothly vibrating well above the audio range, its signal can even be modulated for voice transmission by varying some circuit element. Tesla's few published notes on modulation describe crude ways of varying spark gaps, but, conceivably, an inductance core mechanically linked to a loudspeaker transducer might modulate the signal with some fidelity. Tesla and his supporters waged a fight for recognition of Tesla as the founder of radio. The struggle was finally won in the Supreme Court, but this did not happen until shortly after Tesla's death. Tesla versus Hertz. Tesla was not a theoretician by calling, but he made plenty of observations on the electrical nature of the universe that put him at odds with official theory. In fashion then, and even now, was the theory of Heinrich Hertz, an interpreter of the physics of James Maxwell. Hertz explained radio propagation as transverse waves akin to light. Tesla was convinced that radio disturbances were standing waves in the ether akin to sound. When you drop a pebble into water, the disturbances you see in the form of concentric circles are standing waves. Both Tesla and Hertz assumed the existence of an etheric medium, but differed as to its energy transmitting properties. Tesla believed that the ether was a gas-like medium, that electric propagation was very much like that of sounds in air, alternate compressions and rarefactions of the medium, and that Hertzian waves could only take place in a solid medium. Tesla once said that Hertz waves are radiation and that no energy could be economically transmitted to a distance by any such agency. He said, "In my system, the process is one of true conduction which can be effected at the greatest distance without appreciable loss." When quantum physics and particle theory came into vogue, the etheric medium was dropped out of electric theory altogether. But Hertz's theory was more compatible with the new concepts of propagation and therefore survived. By way of rubbing this in, the unit of frequency, formerly cycles per second, CPS, was renamed in honor of Hertz, HC, while only an obscure unit of magnetic flux density remembers Tesla. It is in respect to Tesla that I have reverted to the old unit in this book. Hertzian radio is straight line. Light-like radiations that bounce off hills and mountains. Long-distance Hertzian transmissions are explained in terms of radiations bouncing off a radio-reflective upper layer called the ionosphere. Tesla thought this was all nonsense and declared in 1919 that Hertzian thinking has stifled creative effort in the wireless art and retarded it for 25 years. Hertzian radio is aerial. Most of us are conditioned to thinking in terms of aerial radio, the airwaves, on the air. Tesla's radio is grounded, the lower end of the energized coil is rooted in the earth. Pure Hertzian radio has no such natural load. Tesla doesn't speak of antennas as such. The element he places aloft is an elevated capacity. Tesla said radio devices should be designed with due regard to the physical properties of this planet and the electrical conditions obtaining in same. Grounded radio is indeed more powerful than the Hertzian aerial, but this is true particularly for the frequencies Tesla was using. The higher frequencies do behave in a Hertzian manner. Yet grounding is all but a lost concept in consumer electronics. Up through the 1940s, AM radio receivers customarily had a terminal one was encouraged to connect to a cold water pipe or other deep earth connection. Ground the chassis of any of today's receivers, and, unless there is some kind of interference coming up through the ground, from fluorescent circuits, light dimmers, which are oscillators, or from the local Tesla coil, you will usually improve signal strength and range. Among Tesla's contributions to radio was remote control. Tesla demonstrated a radio-controlled boat before crowds at Madison Square Gardens and sent another robot craft 25 miles up the Hudson River. Grounded radio works particularly well through water. Tesla's basic radio tuning tank circuit for receiving, coil plus capacitor between antenna and ground, was, and is, all by itself. A powerful signal amplifier, and a beautifully simple one, at that. But as radio developed over the years, the tank circuit shrank in size and the result was a loss in gain. This was compensated for by the addition of stage upon stage of complex amplification circuitry. Tesla watched this development with bewilderment. Tesla knew that the most efficient long-distance radio took place in the lower frequencies, especially those close to the Earth resonant frequency. Frequencies well below the AM broadcast band were the favored ham frequencies in the early days prior to World War I. In fact, waves of 600 meters, 500 kc, were considered short, while considered fairly long were the waves of 1,200 meters, 25 kc. Like a lot of good real estate, many of these more radio-effective frequencies below the AM broadcast band have been appropriated for military use, but also for navigation beacons, weather stations, and time registers. Underground radio. The mind conditioned by Hertz and aerial radio concepts has trouble grasping the idea that signaling can take place without any above-surface antenna, totally through the ground. James Harris Rogers, taking a cue from Tesla, circa World War I, built a radio system in which both sending and receiving antennas were sunk completely into the ground or submerged in bodies of water. He found this system far more effective and far less vulnerable to interference than any aerial radio. Signal strength has been said to be 5,000 times stronger. The military is on to this, as evidenced in the Navy's ELF and Bayou-S. Air Force project underway called Ground Wave Emergency Network. GWEN is a low-frequency communications system designed for use during a nuclear war. The network will have a cross-continent series of 600-foot diameter underground copper screens connected to 300-foot towers reminiscent of Tesla's Wardenclyffe. Among the advantages of the system is its invulnerability to the effects of the electric pulse sent out by nuclear blasts. Such a pulse fries at one stroke any and all solid-state electronics within its extensive range. Strong electric vibrations from a Tesla coil or magnifying transmitter have a similar effect on solid-state and will scramble or disable such circuitry temporarily or even dud it permanently. It's revealing that for last-ditch doomsday communications, the government reverts to Tesla's grounded radio. J.P. Morgan sinks Tesla. Tesla's ambitious world system came to an end when its principal financier, J.P. Morgan, pulled the plug on funding. Morgan, the financial giant behind the formation of many monopolies in railroads, shipping, steel, banking, etc., was a major conduit of European capital into U.S. industrial development in the robber baron era. He looms large in Tesla's life. Morgan money was in the Niagara Falls project. He backed Edison, too. It was Morgan's pressure on Westinghouse, whom he also financed, that caused the cancellation of Tesla's $a horsepower contract and the loss of millions in royalties to Tesla for his polyphase. When Tesla's lab burned down, arson was suspected. One of Morgan's men promptly arrived with aid, as well as with the offer of a partnership with Morgan Interests. Acceptance would have put Tesla firmly under Morgan's control. Tesla refused, and Tesla succeeded in preserving his autonomy until he became possessed with overwhelming ardor to fulfill the dream of his world system. Tesla was ready to sell his soul to finance Wardenclyffe, and J.P. Morgan was right there to buy it. In 1901, Tesla signed over to Morgan controlling interest in the patents he still owned, as well as all future ones, in lighting and radio. Morgan then put about $150,000 startup funding into Wardenclyffe. Later he invested more, just enough to bring the project within sight of completion. Morgan then became elusive. Tesla tried desperately to communicate with the investor, but to no avail. When word was out on Wall Street that Morgan had withdrawn support, no one would touch the project. This finished Tesla as a functioning inventor. Work on the Wardenclyffe Tower came to a halt. Left to dereliction, the tower remained only as a curiosity to passers-by. During World War I, the tower was unceremoniously dynamited to the ground. 14. Lighting. In 1891, Tesla said that existing methods of lighting were very wasteful, that some better methods must be invented. some more perfect apparatus devised. Tesla went and did just that. Yet, here we are today, in a world lit predominantly by the same Edison bulb. Edison's bulb burns with 6% efficiency, the rest going off as heat, while the high-resistance filament cooks at 4,000 degrees and eventually breaks without warning. Today's fluorescent tube, though inspired by Tesla, is no model of efficiency either. Its inner surfaces are stimulated to phosphorescence by energy-consuming filament-like cathodes that also burn out, and the lit-up tube would present a dead short to the current if it were not for the so-called ballast transformer, an inductance placed in the circuit to oppose and thus eat up yet more current. What sent Tesla into an exploration of high-frequency phenomena was his conviction that these rapid vibrations held the key to a superior mode of lighting. The explorations were not Tesla's first venture into lighting. His very first U.S. patent, 1885, is for an improvement in the arc lamp. He used an electromagnet to feed carbons to the arc at a uniform rate to produce a steadier light, number 335,785. Early arc lamps produced a brilliant blue-white light, good for street lighting but not for the home, and they emitted noxious fumes. Home lighting was by gas. Street arc lighting used series circuits. Edison introduced the parallel circuit, and designed his lamp for such a circuit. Edison introduced the big-scale production and sale of electric power itself on the model of gas lighting, a major industry at the time. He wanted to be first in the business and announced to the press that he had an operable bulb before he actually had a bulb that worked. When Tesla's AC system was established, it was grafted onto Edison's, greatly extending its range and efficiency. But, essentially, it was still Edison's parallel circuit, high consumption, incandescent lighting system, and this is what we have to live with today. A better way. Tesla patented both his spark gap oscillator and his Tesla coil specifically as power sources for a new lighting system that used currents of high frequency and high potential. Lest you get the impression that a lone genius named Tesla invented this new form of lighting out of the blue, you should know that others before him had used high frequencies to stimulate light, and others, like Sir William Crookes, had done the same with high potentials, but Tesla was the first on record to put the two together. In Jules Verne's 1872 novel A Journey to the Center of the Earth, the narrator tells of a brilliant portable battery lamp used by the underground explorers. The device was powered by a Ruhmkorff coil, a high-voltage buzzer-type induction coil, step-up transformer, popular among early electrical experimenters. The Ruhmkorff coil stimulated a lamp, type unspecified but probably a gas tube, which produced the light of an artificial day. The lamp had such a low current draw that the battery lasted throughout the subterranean adventure. Verne evidently was drawing, at least in part, on experimental knowledge of his day for what he calls this ingenious application of electricity to practical purposes. Perhaps somebody should reinvent such a high-potential lamp to replace today's flashlight, which seems to exist for the purpose of enriching the ever-ready division of union carbide. Modern neon lighting is high potential at 2,000 to 15,000 volts. Neon sign transformers are good for powering Tesla coils, but a low-frequency, high-voltage device, caution, neon, as well as its cousin, 7,500-volt cold cathode, filaments, fluorescent, which is used in some industrial lighting, is as close as we get to Tesla lighting today. Circa 1900, Tesla experimented with luminous tubes bent into alphabetic characters and other shapes. Although today's neon is simplistic, Tesla, being driven by 60-cycle high-voltage transformer power alone without the benefits of high-frequency excitation, it should suggest to us the amazing efficiency of high-potential lighting, since a single 15,000-volt neon transformer drawing only 230 watts can light up a tube extending up to 120 feet. How superior is the economy of Tesla high-potential, high-frequency lighting over Edison incandescent? Tesla says certainly 20 times, if not more, light is obtained for the same expenditure of energy. 15. Pure light. Tesla invented a variety of lamps, not all of which show up in his patents. He lit up solid bodies like carbon rods in vacuum bulbs, or in bulbs containing various inert gases at low pressure, rarefied. He noted that tubes devoid of any electrodes may be used, and there is no difficulty in producing by their means light to read by.